in this video, I'm going to show how we are going to use GitHub and also use Python to extract data and post the analysis, do the post analysis for the data obtained from the remote system. So before we start, we need to find out where the existing repository is located. So the way of looking for our case now that we'll be working on is particularly the e-watering project. So in my current folder, it is located at C users UQCZen and my e-watering locations. So in that case, I could maximize this window and then right click in there. So you will see that I've already have git bash installed, so I can bash from there. So what does bash here do is that it will synchronize your local e-watering repository with the one that is online. So if you are using GitHub, you will see that we do have a ColumnPy project. So it's just on the process of loading, I guess. Why it's not coming up? Why the internet connection? That's the problem. So I activate the internet connections. Right. I don't have to do that. Okay, so then you will see that I've got my GitHub here, and ColumnPy is actually a system that we've been maintaining, and obviously the files within the web page might be different from the one that you have locally. So the first thing is to synchronize it, and the way of synchronization is by git pull. And after the git pull, they will tell you that this is already up to date. And I also, in some cases, you have local changes, and you probably want to push the local changes to the system. And the way of doing it is to first do git diff. So that will show the difference between the last online version with your current version. So currently, it doesn't return anything, which means the current folder is exactly the same. So the second thing that I normally do is Padrino. So let's say try. No, so try. There's no try, so I probably have something called Padrino somewhere. So if I open up my Spider, then you will able to see you will be able to see the locations where the folder is being located. So this is ColumnPy again. This is ColumnPy. Oh, okay. So I have a way to find out where my current Padrino is. So I just need to went to this PC property, and then advance the system, because I've already put the Padrino into the system. So if you look at the environmental variables, you will see that it's actually uses my name, demo, and Padrino. So that's actually where it is. So then you also need to go to demo and Padrino. Okay, so now I'll do a git pull to update my Padrino to the latest version. So as you can see now, I've already got some changes. Even it's not related to your project, you still can revise it. And then the advantage of using Git is that you basically upload all the changed files instead of individually updating, and you only have one instance within the system. You wouldn't say Padrino, Padrino 2, Padrino 3, and Padrino 100, which is very clumsy, and that's why Git is very useful. Now, we basically ensure that Padrino and ColumnPy are already being updated. So then we opened up the interface. So the place that we will be working with is somewhere the e-watering address is located. So this is where my e-watering address is. So within the folder, what you will see is that I've got a few locations, so Python file and a few photos, so that's the on-site photos. And within the Python folder, I've got 3 Python files. So to be able to run it, the way of running it is to start with the get data python3.py, so that file. So we'll probably first run and see whether everything is fine. So now it's running. The critical part that I want to emphasize here is that when you run the file, you need to ensure that the running folder is at e-watering, not in the Python folder. The reason we decided to do so is because that we don't want one file comes with all the inputs and outputs, which is very clumsy. So basically, e-watering is where the root folder is. If you are looking for a Python file to run, you go to the Python folder. If you want to generate outcomes, you put it into a separate folder. So in that case, the working directory is relatively clean. So in this case, you could quickly do run file, and then do that, and then put a slash. So basically, you run that Python file, but your working directory is in here, right? So then, if you run that command, you'll be able to see that something is coming up. A lot of stuff is going on. So you come up with a lot of graphs, and this is a little bit, clumsy as well. I'll later on teach how we can pop this one out. So the command that we need to run is matplotlib qt. So if you just put this command in here, next time these tiny figures is able to hop out. So I'll show you what actually each graph is doing. So first is that we got all the libraries loaded, and then the Padrino path is basically tell where your Padrino is installed. So if you run that separate command and then look at the individual variable outcome, so that's exactly where your Padrino is located. Yeah, and then you can print it out. And later on, what I did is to update the ThinkSpot to Pandas Python 3. So that's a library I imported. So then once you import it, there will be no issues there. Now, we've got a TB Pandas that is created through a JSON file, which we will have a look at it. So after you run that, you will be able to create an object that is called TB Pandas, and it has a lot of functions. So the function, so first look at the TB credential JSON file. What it has is comments. So comments will tell is just to show what each thing means for. So it's just for comments purposes. ThinkSpot address is where your data comes from. Username is the account that is used for extracting data. And this is the password to getting the data. Every every project has a lot of keys like temperature, humidity, water pressure, and everything. So if you want to get all, just use all. So key comment says that if it's equal to all, that means everything will be extracted. So the start TS and end TS tells you that in which section you need to check the data. And the other important thing is that limit. So if you want to extract all the data, just put this one as empty. In that, if it's empty, then it will extract all the data in between this period. And also bear in mind that you need to ensure the format of the dates is being recorded in that way. Finally is the device ID. So this one needs to be obtained once you log into your ThinkSport. So this is basically the way how you get pandas. Now, if you get TB get tokens, then you are able to get all the key information. So let's say if I run these two commands, you will see from the system that TB pandas, then you've got the key list, key. So you got the does it come up with keys? No, it doesn't have. No. It should list get keys. There is a variable that actually store all the keys, but I just didn't remember where it should be.
Just check the file called TB pandas. The ThinkSport pandas P13. Check the file. Maybe you can find it.
Yeah. Well, you find it from there. Yes. Anyway, so that's not important. It's just a function to use. We don't need to look into the details. Okay, so then you could get data. So once it's been getting data, the data is actually in a format of JSON. So result JSON, and this is huge. This is huge, and it's not easy to manipulate. And usually what we would like to play with is not a JSON format. It's actually pandas format. It's called data frame. What does data frame mean is that it's pretty much like a spreadsheet where you have X rows and Y column, and it's relatively easy to do multiplications and divisions across all the data. So in this case, we need to convert this into a data frame, and that's actually what this command is doing. So once you do that, you will be able to see that the result, say df, result, df, these are all panel data, which is very easy to play with. But just bear in mind that every single, so if I just use this command that shows all the lists of the variables, every single variable will have their own time frame. So let's say if we got a moisture sensor that measures once per day, and we got the weather station that measures every 5 minutes, which means that the length of each data is not the same.
Yeah.
It's not the same. But that makes the post-process very difficult, because if you want to write something as a function of wind and moisture, you probably not be able to find out the corresponding data because the length of each data is not the same. And that's the reason why we need to do the post-processing here. Okay, so now if we move to another one, so this is the schedule JSON. What does schedule JSON do is that it will give a project name. It will provide a starting time and end time, and also the delta TS. What does this mean is that we are aiming to merge all the data, or let's say interpolate all the data, so that all the data with individual timelines will be synchronized to a big matrix, X rows, Y columns, and every single time if you want to do post-processing, you are always able to find out the associated data to do multiplications and minus. And the delta t is basically the interval in between each data. So currently I'm setting 10 minutes for interpolation. So that's basically the meaning of the schedule JSON. And then after we run this, you will be able to insert the input inside the Python file. The reason that I don't want to put those things into the Python code is that we are trying to avoid hard coding. What does hard coding mean is that you try to put input conditions inside the code. It's pretty much like Microsoft create Windows. Instead of saying username, they put actually Tom or John inside as a variable, and that's not a good way of doing it. So you're always trying to put the input outside of your script so that it's relatively easy to be used for other projects. Yeah, so basically if you have something new to create it into the JSON file, not actually in the Python script. Now, so if we try to do these ones, so this is just to add some further libraries inside the Arduino. One of the things that I want to show you is actually constant. So this is a very useful constants that I normally use. So for example, I've got G, P, KG. So what does this mean is that it's actually to, if you have a value, let's say 1 kilo, and you want to convert that into grams, then you can just simply do that, because this 1 actually means 1 kilo, and GPKG means that G is in numerator and the kg is in denominator. So once you convert that, you basically get a value that is 1000 G. And it's relatively easy to see, so you know the reason why you use that conversions. I've seen a lot of code that just multiply by 1000 divided by 0.001. You might be able to understand it when you are programming, but after 5 years, you forget about it. So always try to use constants to convert those variables. If there is no within constant, just add it. So later on, you always know the reason why you need to do the unit conversions. Now, I've got the SPSCH here. So that is to create an empty box. And I've already got the starting time and ending time, so you can search it later on to see how the empty boxes are created. But nevertheless, you can do SPH, and then so index df index. So this is the empty. So now this is pretty much like a spreadsheet, but the spreadsheet only has got one column. The one column only has got the time. So you can see that the time is always every 10 minutes, correct? Yeah, but there's no properties. And then we try to interpolate our monitor data into this X row, Y column spreadsheet. Now, what we're gonna start with is UV. Okay, so what does this one here mean? So SPSCH, merge data from TB. So that means merge data from ThinkSport. And then what we need to get, the x-axis is the time when the UV is being measured. The y-axis for the raw data is the value of the UV. So both of them are raw values. And then what is the interpolated result is actually DF index, which is actually here. And then once we want to merge the raw data into our matrix, we want to name the key values to SA2 underscore UV. You can put it to something else, let's say solar intensity or whatever. So it's going to be different from the original name that we use. Okay, so plot means that you want to see the result straight away. And we've also got a coefficient. So the coefficient is to see how smooth you want to get for the interpolation. I'll show you how the result will be changed after we do the interpolations. So RMNaN is that you will delete all the not a number within the interpolation. So I'll show you how I do this. So I copy C here and copy paste it there. So I just do some updates. So you will see a graph comes out. So this graph is relatively difficult to see. So what you can do is that you open it up and then you try to zoom in to the specific area that you want to see. So you can see that the blue dots are all the raw data, but the red dots are only into a small section of it. The reason is because I ask the interpolation just do this area, not beyond that. So so currently you see, so let's go back. So currently the system has already been running to April 14th, but my schedule only asks me to do up to, so if you look at the lower left of the screen, you will see the time when the cursor is when the time of the cursor. So basically, it says that it finishes at 7th of April. And if you go back to your schedule, that's actually being requested here. So that's actually in which section you want to do the interpolation. So if you do it longer, you will end up there. Yeah. And the way to check the results is to basically zoom in. So you can zoom into this area. So one of the things that you probably, one of the things if you want to make it even better is that you look at there are a few dots that doesn't really make any sense. So you probably can delete it before you do the interpolation. So the way of doing that is that you can use a line of code, which I've already done here. So you see TB pandas, which is the raw data. And if the raw data, so now we are talking about SA2UV. Okay, so if SA2UV value is larger than 60, then it's just make it as a not number. So currently, we are targeting the numbers that is more than 60,000. So we need to convert that number into 60,000, yeah? Okay, so now if we run this, that means the raw data with a value larger than 60,000 is going to be disappeared. And we can do another interpolation with the revised raw data, and then you will see that this graph is no longer there. Yeah, so now it's the time for you to check the consistency. So if you, the key thing to check the consistency after interpolation is to see whether the peak has been reached and also whether the graph is relatively smooth. So the solver is relatively able, the interpolated result is relatively able to capture all the points that we measure. So that's actually a very good interpolations, yeah? So then you feel, oh, that's probably okay. So then we can switch it off and then do the next one. So for the next one, let's say, you know, I have a reason to get rid of some of the data, but I would like to see the reason. So I will probably do the interpolation and you will see the reason why I need to delete all the numbers that is larger than 60. So I can copy this one and you will see, oh, there is, so we are talking about a temperature, but one of the temperature is already gone up to 100 degrees Celsius. And you don't want that noisy value to affect your results. So what you do is that you first delete that guy. And now, if I run this again, the result is not going to be affected by that noisy guy anymore. Does that make sense?
Yeah.
Yeah, okay. Now, there's also something very, very important. So I'm talking about the smoothness of your graph. So, you know, I put the graph here. So the coefficient we used to do this graph is 5 power negative 8. So how about if I increase that number? So I'll do another one. Let's say instead of doing -8, let's do -14. And then repeat the whole process. And you will see that this result might not be the one that you're after. Look at the differences. So if it's negative 14, it means that the curve becomes relatively rigid, and so it wouldn't be able to reach the maximum value. So in that case, the negative 14 is not really the right coefficient to be able to use for the interpolation. So it's basically your eye judgment to be able to see whether the interpolated result is able to be representative to the data you have monitored, and also ensure that all the data is sitting in the one timeline so that later on you can do manipulations. You just want to ensure all the data is at all the time points and make a perfect spreadsheet, and then you can do all the analysis. And also I can give you another example. So let's say I try to make this number relatively large. So instead of negative 8, I'll do a negative 5, yeah? So you can immediately see the difference. So it's here. So I could compare that to this. So at least from this graph, these two looks quite similar. And also an interesting part is that this has got a bit mixing dots, and the interpolation is able to somehow fill the gaps in between of them. And that filling is all depending on the type of variables you choose. Yeah, so that's also our advantage of using interpolation. So that could somehow fill a natural gap to be able to stitch all the data all together. But in some cases, if you choose this number too small, there are too much wigglings in your graph, and then you don't want that to take place. So use your eye to judge which one is better and which one is not good. But the key thing is that when you zoom in, you see that it actually follows the lines, and that's actually very important. Now let's just move further. So in humidity, there is nothing interesting, so I just ignore that. Okay, so this one seems to be very, very interesting. So I'll show you some of the things that I did here. So before we check why we need to do this, let's just try to run this command and see what is the problem. Because when you look at the new data, you probably first directly check and see what is the problem. Now, after you run this, okay, so I need to make the plot as true because I want to see the results. Yeah, I want the plot comes out to me so that I'm able to see it. Now, again, this one is, there's a graph that is huge and we need to get rid of it. But before we get rid of it, I can use the interactive way to look at the data. And you will see that it's not too bad. So, and I can further zoom in and to see that, overall it actually catch up with the results. But there's one interesting thing here. Now, which is the right value to get rid of the noise here? Now, you see that this line, this dot, is actually slightly higher than the dot here. So let's say if I write a command to say if the number is more than 1, let's say 0.8, let's get rid of this guy. Then in that case, you are not only get rid of this tiny little dot, but you also tip this one as well. And you don't want that to take place. So what I did here is that I try to compare the difference between the neighboring values. So that's why I use the NPDIFF. If the delta y between the neighboring value is more than 0.5, that means this is a noise and get rid of that guy. So basically, if you go back to this graph, you will see that probably the previous value of this is nearly 0, and now it goes up to 16. So the delta t is 16, which is more than the 0.5 I have it there. So it's a noise, get rid of that noise. And this is the way how we are able to clean the data. So now I've already cleaned the data, and then I can show you the difference after that. Look, it's beautiful, isn't it? So then you can basically zoom in and see. So it's just to find out the right way and using commands to get rid of this kind of wrong measurement, and that's always taking place. And you need to make it relatively smart, and so that you can further just interpolate the results based on that. Now, I'm not going to go to all these details, so you see that this one has got the similar things that I need to delete some of the fluctuations inside. Just double check whether there's anything that also here you can see I tried to convert. So this is something that I did interestingly. So let's just run up to here. So the way that you can run up to some stage is that you select all the codes and then right click, say run cell. So that actually means that it runs up to this line. Yeah, so now that's why it's coming up. It comes with a lot of graphs, unfortunately. It seems that it's not running properly because the rest of the things needs to be displayed. I'm just trying to delete these guys and run it again. Okay, so let's run up to here. Run cell. So there are a few things coming up already. See, that's where we are. Now, I want to show you how we try to get a rate out of that. So now, an interesting thing that we need to get, so we've already gone through that, we get rid of this. So this is actually the water level monitored from a side. Now, instead of looking at the water level, I want to see the increasing and decreasing rate. So literally, the right term to do that is to calculate the derivative of this value with respect to time. And the way how I did it is that I used the MPDIFF to find out the difference between the neighboring value. But after I do that, you will see that your matrix is one less than the original one. Because you have 3 values, you get the difference, you only get 2 values. You wouldn't be able to get the last one. Yeah. Then you need to append another number to make it the same size as the entire matrix. Otherwise, the matrix is not going to be a beautiful one, right? Yeah. And you divide that by times per second, which is a variable. And usually, when you look at the rate, particularly for the hydrological process, you're not looking at meter per second. You basically look at millimeters per day. So you convert that to millimeters per day using that value. So then, unit is properly calculated. Then I copy that line. If you look at these lines, after 5 years, you understand exactly what you're doing. Yeah. You don't convert that by 96,600 or whatever. Then what you could do is that I wrote a small graph and small script to be able to show the graph, what the graph looks like. So then I click that, and it comes with a graph, I think. Does it pop out? It hasn't popped out yet. Okay, so then I could do this. And then I'll say FIG show. Does that come out? Yeah, okay, so that comes out. So this will show you the rates of it. So you will see that at the early stage, it's actually increasing. The rate is very high. But later on, once it moves to the next section, it's actually decreasing, which is the reason why this value becomes negative. Yep. one of the things that I need to mention is that you will see that these two graphs shows a relatively different, even the pattern looks the same, but the intensity is different. One thing to bear in mind is that the intensity here is more or less related to the type of interpolation function you use. So be very, very careful when you're using the interpolation. Interpolation is very important because without interpolation, if you zoom in this number, so let's say, well, in the natural condition, what happens in this area is that we stop pump, and then water is basically either evaporating or recharge. So we're supposed to have a pure decreasing trend, not having any increasing trend. Interestingly, if you just zoom in, what you will see is that sometimes it actually increases. So you definitely need to have a smooth function to be able to get rid of this noise, because in the real field, there is no sense that water is able to gain from somewhere. Yeah, so that's why interpolation in here is extremely important to get rid of the noise. But again, to be able to interpret it properly, the curve could go in this way, could go even in this way, if the interpolation is too wiggling, which means that you choose a relatively large coefficient in the first place. So you need to basically find out the right coefficient in here, which would be the best to tell you the overall trend of the data. Does that make sense?
Yeah.
Okay. Now, so that's here. I've already done a few other things here, but I think the rest of them is nothing particularly interesting. So it's just to repeat. So I would suggest that we always check the data visually and then use a specific coefficient for each of the interpolation. Okay. And then we are able to get a decent data. So in terms of this, so there's also another interesting thing is that this section is that I try to find out the time range, and I get rid of the data within that range as an odd number, because that range, the interpolation doesn't make any sense. So I probably can show you. So what I can do is that if I do this one as true, I do an interpolation, and you will see that some of the data might not make any sense, like this area. It doesn't make any sense. So in that case, I basically ask, so it's from the 1st of March to 18th of March. So 1st of March of 18th of March, which is here. So did you see that this graph, like the yellow one, the red ones? I can't use it because it's actually an extrapolation. Yeah. So I need to get rid of that. I don't want this one to be part of my outcomes, right? Yeah, yeah. So then what I can do is that I find out this is the starting point, this is the ending point. I'll just do that. I'll just kill it. And now if I look at the clean data, I think I probably can just do it from here. You will see that I wouldn't have any kind of very abrupt change afterwards, yeah? So that's, some small things that you could do to get rid of the wrong data within your graph. And the rest of them is just to clean all the data. So what I'm doing now is that I just probably run it. Also, that one of the habits that I tend to do is that I try to limit all the codes within this line so that it will be much easier to be printed. So if you want to go to the next line, then you use the reversed slash to have a continuation. So probably for now is that I'll just save this and then run it. So I'll just say run file. So I just put run and then use the upper up key. Then it comes with the command. So I just run it. Then of course it comes with a lot of graphs. But later on you can just change the plot interpolate as false, as false. So you wouldn't need to repeat to see all the graphs once you you know this set of graphs is okay. So I close all the windows. Now, this is just to interpolate the data. And if you use SPSCH result, DF, this is where the clean CSV file is located. So probably I can do 2 CSV. Then you will see the data looks really beautiful. So let's say result CSV dot and CSV. So if we want to basically extrapolate, if we wanted to further look at the data using spreadsheet, for example, it's here. So then you see the result CSV, 2 megabytes, opened it, and you will see the result just looks like a beautiful XYZ graph. Yeah, and also the title is on the top. Yeah, much easier to do the post-analysis. Now it's a matter of drawing graphs. So I've already run this, so I don't have to repeat. So the second Python code that we need to look into, so let's look at the list of the Python code, is to produce video. Yeah, so let's do here. It's pretty straightforward graph producing, but there are some things that I need to pinpoint. So basically matplotlib and images and also get the date taken. So this is actually to check the photo images and to find out when the photo is being taken. And also I give the name and the location of the image. And then well, this is a little bit hard coding because I just was in a very much haste to get this one down. Yeah. But it's always important to put these ones into your JSON files and also ensure that your photo location is the same as I have. So, so that's where my photo is located. So this is something, we always need to ensure that the program is able to run at different computers. So, so the SA photos, the variable needs to be different from myself. And then after this, so let's just copy this section. So I use run cells to run up to this level. Okay, so this part is to find out all the file names and also list them. So after running this, I'm not going to do all the details. You will see that file name SA2 basically ends up with all the list of the JPG files within that folder. And then we have some parameters to do the plotting. And I can copy it. And then I have the for loop. So this is a huge for loop. And then the for loop is run by the number of file name. So I've got 2 images, and then I give a relatively right number of spaces to do the plotting. So here is 7 rows, 5 columns. The first row, first column, and then this is the second column, second row, second column, and then that's basically the location. And these 2 means that this 2 is the plotting area for the picture, but even though it starts from the first column, the first row, 5th column, it takes up 4 rows and 3 columns instead of having that tiny little cells. And then I'm able to adjust the spaces between each plot to make it small or make it large. And this line is to adjust the margins. So probably you want to make use of the space so the margin is relatively small. And this bit is to make the boundary lines of the plotting thicker. So the width is being increased. So the first is to plot millimeters per day. And the peak potential evaporation rate millimeters per day. The second plot, so this is the first plot, this is the second plot. So the second plot is pounding falling rate for different type of census. and I also have the vertical line to indicate the current time. Because I'm showing the pictures within the graph, I want to indicate that when the picture is being taken, and that is being showed by the V lines here. So we just repeat this whole processes to be able to plot all the results and sets the Y limits. I also put the grades for the graphs, and I also show the graphs pictures within the plotting area, and I also change the formats of the x-axis and also the y labels. We put the legends, and then those goes into a big loop. So now I'm trying to delete all the produced graph. Let's say this is the round results. So I just delete them. And instead of running all of them, because in the very first time, you don't want to produce all the graph, because the very first one is good enough to tell you all the results. So what I normally do is that I say that from 0 to 1. So that basically, the loop only run once. And then I could use run cell to be able to get the results. So the key error is millimeters per day. So what is that? So the PET millimeters per day is not being executed properly. So probably this is because of the PET somewhere. So basically PET is not being, so I probably run something, but it's not being, I think it's ET millimeters per day. Oh, it should be PET actually. Ah, okay, so this is actually the weather station data. So I need to run the weather station calculations first. So the second thing that I did is calculate evaporation. So this is actually the second graph, the second code that I need to run, which basically converts weather station data to evaporation. But this is literally just use Penman-Motis potential evaporation rate calculation. So you just need to go through that to see how the evaporation is being calculated by weather station. So I've got something already. So just leave that for now. So this is also the graph from the last. So I've already got the PET. Then I can again do the videos. So I'll just right click and then use the run cell. And now they will say that the PET is already there. So yeah, so that's what the result looks like. Yeah, so it has multiple graphs, different times, and also 2 graphs to show the recent time. And also we need to somehow make this line pretty much aligned so that it looks much better. So I think it's also being saved as well. So saved means that it's here. See, this is the recent result that I got. So if I try to increase the number of productions, I simply need to change this into 5. So if I change this to 5, then we'll produce the first 5 graph rather than the whole thing, because the whole thing could be 20. So it will be too much. You probably just do a quantity check and then automatically produce the rest of them. So you see it's slowly coming up. Yeah, so, and also the problem currently we have is that the timeline is not aligned very well. So we need to adjust them properly. This is not very clear.
Why is it happen? Because you have to interpret all the data.
I don't know. We need to check. We need to check. One of the reasons probably was that, well, if I set x-axis from sometime to sometime finish, then it should. It's just some plotting issues. So it should be relatively straightforward to fix anyway.
And because you have interpreted all the data.
Oh, okay.
But why
I
some
see.
data are missing here?
Then we need to find it out.
Okay.
We need to find it out. I think I know the reason why this one is not, because I didn't do the interpolation for the EC.
Okay, yeah,
Because EC
yeah.
for me, I don't really need to.
Yeah.
I didn't write this one as a function of something,
Yeah.
so it's raw data. It's
Okay.
basically plotted up to today.
Okay.
Yeah.
So maybe the potential evaporation rate is also that based on the raw data, right?
No, potential evaporation
But
is
I know
not.
it's based on, it's calculated with the raw data.
No, it's not.
But why there is a missing on the
I don't know.
reason, yeah.
I don't know. We need to
Okay,
find
yeah.
it.
Yeah,
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 we need to
find
find it.
it,
Yeah. So that's just a very quick crash course on how you can
Yep.
extract data from ThinkSboard,
Yep.
combined with images to produce a decent set of pictures that can stitch together as a video. That's all about it.